Hello everybody. Today we're going to be talking about finite element analysis, or FEA for short. So what is finite element analysis? Well, FEA is a numerical method used to solve complex stress analysis problems. It basically takes the idea of chunking, which is breaking down some complex task into more simplified tasks. So think of, having to read some large dissertation and maybe the author was kind enough to provide you with subsections. Well, it's a lot easier to read just one subsection, get through that one subsection, and then it's easier to get through one more, and then by the time you've done all of them, you've completed the entire paper. Well, similarly, FEA will take down a very complex part. It'll take a very complex part and break it down into smaller, more simplified parts or elements. So each element is then solved individually and it's reassembled back into the whole part to gain an overall solution for the part. And there can be hundreds or even thousands of elements, but as the name suggests, there should be only a finite number of elements. So let's go into a little bit more detail. When a part is divided into finite elements, FEA relies on applying fundamental engineering mechanics relationships to each individual element. So when analyzing the loads experienced by a given part, the force, the stiffness, and the displacement of each element will be considered. And the analysis will then be extrapolated back onto the larger part after they have been solved. So typically, force and material stiffnesses are already known parameters in a given system. So usually the desired outcome is the displacement of each individual element. Typically, this is done by way of a system of equations in which all of the elements have an equation associated with them, and then a system is developed with each individual equation, and then the system of equation is then used to solve the problem as a whole. So let's talk about meshes. Within FEA, there are two major components, and these components are geometry and material. So a part should already have been modeled in a computer-aided design software with very specific geometry, and this geometry is usually very complex. Otherwise, you probably wouldn't be using FEA analysis. You probably use some sort of classical hand calculation method to solve it. So geometry is usually very complex, and once we've got this geometry made, we will fill it with a mesh to represent material properties that are important to the component. So a mesh is made up of many finite elements that have shared edges and shared nodes. So the first step to solving any FEA problem is to design a mesh. Mesh elements can either be one-dimensional, that's usually like a beam or a column. They can be two-dimensional, which is usually some sort of coating or like a shell over a part, or three-dimensional, which is solids. These element shapes can be triangular, pyramidal, cubic, quadrilateral, and the list goes on and on and on. The point is, though, that the individual shape is easier to analyze than the entire component as a whole. So mesh refinement is a really big issue in finite element analysis, and there's really a balancing act in refining the number of elements in a mesh. So if you think about it, the smaller the elements included in a mesh are, the more accurate the FEA solution will be, because the bigger the elements are, the larger your error is going to be in your outcome. And this is really a big problem when designing a mesh for an FEA problem. However, when you have smaller elements, that means you have a larger quantity of elements to fill up the shape, and thus you have a more complicated calculation process, and it can take much longer for a computer to analyze each element. So right here we've got a graph, and this depicts a stress curve. And so what we have is basically the outline of a mesh for each node in a curve. So these points right here represent nodes of the mesh, and as you can see, we may have some large force or stress concentration up here, And if we select nodes in this manner, we're losing a lot of information right here. So it would really probably be better to increase the number of nodes in this case, and maybe we would add one right here, right there. And so we get a more accurate distribution in the end. You get the picture. Also right here, I've got another little representation of what we can use meshes for. So we've got this little part right here, and we know that we're going to have one edge, say this back edge is going to be a boundary condition. It's fixed. It's not moving. But we've got some sort of load applied to it right here. And so usually just based off of traditional mechanics, we know that this inside edge is going to experience quite a bit of stress concentration, but with how big we've got this particular mesh, it may not pick up all of the information that's going right here. So it would be a good idea to maybe, add in some mesh elements here in order to get more information off of the part using that finite element analysis. So there's a lot of different applications for finite element analysis. Generally, it can help determine adequate thickness of material for any part that's in question. More specifically, think about the automotive industry. Think about crash tests with cars. Automotive industry spend a lot of money on making a car and making dummies and simulating a physical crash. And then they've destroyed their part and everything. But if you use FEA on this, you can already use your pre-modeled car, which is usually going to be the case in an automotive industry, and perform finite element analysis on it to see what the displacements are going to be when a car hits, say, a brick wall. Other applications include structural engineering for bridges or trusses or anything that has applied loads on it in any given structure. Also, biomechanics uses finite element analysis quite a bit as far as analyzing the forces that different bones in the body can experience. And even heat transfer. Instead of traditional mechanical stress, we may think of heat fluxes as being a stress on a certain piping system or a heat exchanger that is used in some sort of application. And then there's a lot of popular programs as well that utilize FEA and provide this service for their users. So perhaps the two most competitive companies are Dassault Systems, which is a French company, and Autodesk, which is a US company. And Dassault, they produce the very popular SolidWorks and also its parent property, CATIA. Autodesk, on the other hand, they offer Inventor or Fusion 360, and they've got a couple other ones too. And I think Inventor is quite a bit older than Fusion 360, and it's a lot more expensive. And so there's a bunch of different factors in choosing which program is right for you. Other popular FEA softwares include ANSYS or Altair Engineering or SimScale, and all of these properties, they shine better in different applications, and they really differ between price, ease of use, the particular application, and they should be selected based off of such. Now we're going to talk about programmable logic controllers. So a programmable logic controller, or a PLC for short, is at its core a computer which is designed to operate within an industrial setting. And as a computer, it receives inputs, it processes these inputs, and analyzes them corresponding to a given program, and then it produces an output based on the logic that it reads. So PLCs have largely replaced traditional relay switches, which were manual in nature, and this meant that technicians would physically have to turn on or off switches, and really this based on how many relay switches were needed in a given industrial application, this could be very time consuming and as a result very costly for a company. And PLCs, they're tasked with running a single program in a step-by-step fashion, following the sequential logic written into each step. And they actually have quite a few advantages over modern day computers. Namely, they're more reliable, they're cheaper, and they're faster than modern computers. And perhaps the biggest advantage is that they are reprogrammable. So a new or altered program of a original program, they run in the same sequential manner, step by step, reading the logic of each step. And because of this, because they're only running through one program, that is why they are so much more faster. They're so much faster than modern day computers, and they're a lot more reliable, because if you think about it, modern computers are running tons and tons and tons of tasks at once. And so really this is just the biggest advantage that PLCs have over modern computers. Also, PLCs don't actually need to be rewired, which is another big benefit, because having to rewire a system can be very time consuming as well in the industrial setting. So the ultimate goal of a PLC is really to manipulate a larger system through some array of actuators. And this is the keystone to automation, which really reduces costs for different industrial companies. So now I want to talk a little bit about components of a PLC. So we have made the analogy between PLCs and modern day computers. Well, PLCs don't actually have traditional computer displays that we associate with modern computers. And they also don't have keyboards or other accessories that you can find on your household computer. What PLCs do have, though, is a computer component, and this computer actually houses all of the memory required to process the input, to process any number of inputs given to the PLC, and thereby producing outputs. So these inputs, they determine the logic conditions that the computer will sequence through, and this can be switches or sensors. And then the outputs, they're actually enacted as a result of the logic in the program, and they activate valves or coils or any other number of things that will activate automation, enact automation. Additionally, PLCs have communication ports which actually allow users to interact with the PLC, and this can be at the physical interface of the PLC, wherever the PLC is actually housed, or remotely. And that there again is another benefit of the PLC configuration. And users may want to interact with PLCs to alter programs, modify them, change them, completely redo them to put them with another system, or they can also receive data from the PLCs. And this can be very beneficial as well to get logistical readings and to basically maintain what's going on with the PLC. And also the PLC is housed within a physical rack or a chassis. And what's interesting is this rack doesn't actually have to contain the inputs or the outputs. The inputs and outputs can actually be housed in completely separate buildings, as long as there are data cables connecting the inputs and outputs to the PLC, to the computer of the PLC. And of course you have some sort of AC or DC power supply, and the voltage requirements are really going to depend on the needs of the PLC corresponding to its application. So PLC inputs or outputs, these signals can either be digital or analog, and there's a huge difference there. So digital signals, they only have two possible outcomes, and this is either going to be on or off. So digital signals follow a yes or no logic, in which a given line of of a program conditionally determines the output, or vice versa from the input. So this means that an output can be either activated or disabled, but there's no in between. Analog signals, on the other hand, they present a continuous variation in proportion to some input or output. So there is in between with an analog signal, and an example of this could be some sort of sensor where you're getting a different input into the system. And so as an example, we can show kind of the graphical representation of digital versus analog right here. And so say with the digital we have some sort of input, and the PLC program is reading this conditional program, and the program is telling it, yes, turn this actuator on. So we would be in the on position here. But then the program may reach a point where it's no longer meeting this condition, and it tells the output to turn off, or to deactivate. And so it would go down to the off position. And maybe at some point it gets back to where it's within the conditions to be on again, and it turns back on. And you get the idea. Whereas on the other hand, with the analog, maybe we have some sort of rotating cam system where the cam profile is displacing some sort of piston, and that's really this displacement is driving the output. So maybe we would see a curve like this where the displacement is really high right here, and that means that the output actuators are also extended probably about at their max, and then the cam could come down, the displacement could decrease, and it's continuously variable, so there's always going to be a change in input and output with an analog signal. So now I want to talk about geometric dimensioning and tolerancing, or GD&T for short. So GD&T is a system of rules that's used to comprehensively dimension a part that is to be manufactured. And these rules are actually standards, and in the United States they're set by the American Society of Mechanical Engineers, and in Europe it's set by the International Standards Organization. So at its core, GD&T effectively communicates the intended functionality of a part from the designer's point of view. This allows for clarity of the geometry's function. It also allows for flexibility in the manufacturing process, and it gives a set level of precision for the inspector to adhere to. GD&T focuses on the important relationships between features of a part by putting more emphasis on what really matters within a part. And when we're talking about GD&T, it's really important to understand what a feature is. So a feature is any clearly identifiable physical portion of a part. So this could be a shaft, or a cylinder, or a hole inside of a part. And feature attributes, there are 4 of them. They include size, location, orientation, and form. So size can be measured across 2 opposing points of a feature. So think about the outside edges of a shaft, or the diameter of a shaft. That's a feature of size. And size is actually the only attribute which should be governed by a plus or minus tolerance within GD&T terms. Location references the position of a feature with respect to a datum, and we'll talk about what datums are in a minute. And so location is the position of a feature, whereas orientation references the angle of a feature with respect to a datum. And there's also form, which refers to the physical imperfections of a feature in terms of their allowed tolerances, because no part is perfect. And we referenced datum, so we're going to go into a little bit more detail about what a datum is and how it relates to GD&T. So a datum is an origin from which location and orientation can be measured or established. A datum reference frame theoretically defines the origin of a part with up to 3 orthogonally intersecting datum planes which typically correspond to respective sides of a part. And these planes are always listed in order of importance for the part. So you've got a primary plane, a secondary plane, and a tertiary plane. And each additional datum plane you add, up to 3, restricts the degrees of freedom of the part. So GD&T requires that an entire part be located with respect to a datum reference frame in some given origin. So a datum feature refers to the physical imperfect surface of a part that corresponds to the theoretical datum plane of that part. Highly precise machine tools are used as datum feature simulators to measure, manufacture, and inspect a part. And this ensures that the part is entirely restrained, which means 0 degrees of freedom with respect to its datum reference frame when performing these tasks. It's also important that we go into control frames a little bit. So geometric dimensioning and tolerancing defines the 4 feature attributes, which we just went over: size, location, orientation, and form, by controlling them usually within 2 boundaries. So the control frame is actually a box that's listed, or that's shown on the drawing, and this contains all necessary information to constrain a certain feature. Different symbols are used to control different geometric characteristics, and usually a tolerance zone is provided to ensure compliance of a part feature. And lastly, the datum reference frame is defined by letters corresponding to each datum plane. And we're going to go a little bit into some of the types of geometric controls. So I think the most frequently used of these controls is the position control, and this defines the allowed location and orientation of a feature of size. So position does not actually govern the form or size of a feature. It only can affect the location and orientation of a feature. Position control specifies a tolerance zone around a feature's ideal axis, centerline, or center plane in which its physical counterpart must reside within. So there's some sort of envelope that the actual physical outcome needs to adhere to. And then on the other hand, we've got form, the attribute of form, which can be restricted by different controls such as straightness, flatness, circularity, and cylindricity. Essentially, these minimize the allowed imperfections on a given part surface so that it is as close to perfect as it can possibly be. And lastly, we're going to go over a little example. So right here we've got this part, and we can see right here we've got the datums, the datums listed. So this is datum A, datum B, and datum C. And this is corresponding to this side of the part for datum A, this side of the part for datum B, and this side of the part for datum C. And those are in order of importance, as you see here listed here, A, B, and C. So this is the primary plane. A is the primary, B is the secondary datum plane, and C is the tertiary plane datum plane. And right here we've actually got this is a position control feature. That's what this symbol refers to, and we've got the leader pointing to this hole right here. And so we've got a tolerance of 0.2 that it must adhere to. So as an example, we can say that we've got this hole right here, if we've got these objects, and we can say that this is the envelope, the specified envelope. So overall, the distance from this edge to the inner edge of this cylinder needs to be a total of 0.4 as corresponding to this drawing. So if we go in here and have the actual physical part, it must reside within this tolerance, within this envelope, in order to adhere to the standards of GD&T.